No, but no, it's good to see you again.
Yeah,
And
likewise.
it took a while, but eventually we got there, and
Yeah.
we're having a nice call. Um, yeah, a lot of people reacted on the previous video, which was funny, and we asked them if they wanted uh, more videos about cables and cable technology, and they all said, "Yeah, yeah, yeah, of course we want to." So, well, here we are. Um, yeah, I don't know if you need another introduction, but you can introduce yourself in a couple of sentences and say who you are, what you make, and what your philosophy is. And then we can, I think the first topic would be interesting to talk about the difference in digital cables and analog cables, because a lot of
Yeah.
people are confused about that. So,
Yeah.
who are you? What do you do? And what's your philosophy?
Yeah. So my name is Joakim Juhl, and I started OePhi a couple of years ago, mainly as a cable manufacturer, but now we're also selling loudspeakers. And I would say that like many others in the business, I started as a hobbyist, already as a teen.
Yeah.
Then I had another career, went into research. I even have an affiliation with top universities, such like that. But I just could never not do hi-fi. So after COVID, I made the decision with support from my wife that now it was time to actually make a brand and get it out there. So my background is that I am an engineer. I also have been working in research for more than a decade. I think my approach to hi-fi is both with the ear and I think as well with the technical side. And I think it's very important to combine those two because
Yeah.
on the one hand, what matters to the ear is also what should matter, I think, to the final product. However, the question is also, as we talked about last time, that in many cases we actually don't know that much about the technical side of what then matters to the ear. So we do know certain things, but then there's a lot
Yeah.
of other questions. And I think this is where my research background kicks in because I really love these puzzles. And I don't imagine that I'm coming up with one answer to fix it all immediately. But I do think that pursuing the questions, staying with them for a long time pays off.
Yeah.
And this is what really brought me to make cables the way we do, which was to stay with the problem to say, well, we know that frequency response and we know that total harmonic distortions, those kinds of measurements are not really that different between cables. So we might see small things, but I think it's a far stretch to say that that's the reason we really hear subjectively really big differences.
Yeah, I
So what
agree.
I came to through a lot of testing and research and looking into literature and studying all sorts of various aspects to figure out what on earth is going on was that the best explanation is the time domain performance. So whatever you do to the signal, you will always modify and alter the order of that information coming through the system. And that modification in the time domain is irreversible. You cannot really fix it. So once something has been, distorted in the time domain, that's it. You really cannot do anything about it. So our cables are made from the ground up to minimize the effect on the time domain so that whatever comes through the cable should be treated so equally that the ear cannot tell the difference. And that's obviously a really difficult thing to achieve, but that's what we designed for. This is really what we are here to offer.
And you were talking about the time domain, and I think it's very, very interesting because that's the one point I actually found out in the massive test we did on cables last year, is that cables react very differently in the time domain. That was one of the biggest differences. I mean, like you said, frequency response practically all the same. Minimum differences. Distortion, not really. But in time, there were massive differences. And you can actually hear that. It's the difference between getting a little bit anxious on the couch, like, oh yeah, something is off, and you cannot pinpoint it until you know what it is, and really get into the music and enjoy it. That for me, that was the difference. And I noticed it's the same with speakers actually. there's a massive difference in how speakers react on timing, bass kicks, hi-hats, different layers that actually blend or not. That's the whole point of, I think, timing that is on or off.
Exactly, and the question is always, so to what degree do we need to get it absolutely correct, and then what do we need to do that? And then I think what we almost never talk about in hi-fi, but this is kind of the reality of any engineering field. When you optimize for something, you kind of need to ease off on something else. You can't do everything to the same degree, because that would be not choosing. So I think the question is always, how much is there to be gained, and what other kind of things are you then less attentive to? And this is the same, I think, for all brands. And I think we just never talk about it. We always talk about the things we strive for. But then on the other side, in order to get that, if we want to kind of have absolutely linear frequency response, then in a loudspeaker, you need to do a lot of modifications, the crossover, which then affects the time domain. So
absolutely,
I completely agree. And I think this is a trade-off that we have too little knowledge about. What I did find in the literature was that it has been tested about 15 years ago. There were some scientists at the Technical University of Munich, where they kind of made a setup where they took in a lot of people, not golden ears, but regular people without particular training in this. And then they just wanted to assess what kind of timing differences can they actually reliably detect. And what they ended up seeing was that down to about 1/5, 1/7 millionth of a second was detectable by ordinary ears. And the conclusion was that, first of all, this is probably a more reliable explanation for why we in high-end talk about frequency extension, not because we need a lot of content at a 100 kilohertz, but because the timing, the time performance effects of whatever's going on in the ultrasonic will then actually affect everything within the sonic range to a degree which is far beyond our kind of ability to control, in a sense that we can kind of measure it and then correct for it. And the second conclusion, which I think was really fascinating, was to say that what they found was the threshold of the measuring equipment, not necessarily our hearing's ability to detect these differences. So I think we yet again have to be very cautious about what we think we can hear and not hear. And I think my position is that I never use theory to rule out our ability to hear. Rather, I want to say, well, if we hear something, we need to find plausible explanations for how can we understand that. And this is, I think, the centerpiece of what we do in OePhi, is to understand how is it that we're sensitive to the time domain. It's not that all differences in the time domain matters the same, but certain differences are just so telling that, for instance, that the imaging of the entire system is hugely affected, or how we perceive the timing and the energy of the musicians, separation. And one of the things I'm really proud of is that a lot of people tell me when they hear the speakers and our system when we set it up at shows, is that it just sounds right. And I think we kind of intuitively know something when it's right. It's just that so much gear is not actually quite right. And then we kind of mess about with a lot of things that are just suboptimal. But reviewers and also just people coming through our rooms, a lot of them just say this without having talked to each other. So I do think that there is something about it which is, of course, right. Great to recognize.
But I agree on the fact that if a system is correct, it just sounds right, and it's not spectacular or anything like that. It's just correct. And there are a few brands that I have that feeling with, and people that follow Alpha Audio know what I like. And one of the things is I always compare it to a Christmas tree or fireworks. If a system is very impressive, after a while you get tired, and it probably does a few things very impressively and nice, but other things will get damaged by presenting so impressively. And you have a few examples for sure of brands that do that because they want to stand out in a store or just want to impress within the first minute, and it just gets tiring.
Yeah, and I think that has unfortunately become part of the business of the trade.
Yeah,
that's
the same with televisions.
Yeah. So if you can kind of boost the colors and the perceived dynamic contrast, then in a few minutes you might impress somebody looking at it and comparing to the neighbor screen. However, living with it on a daily basis might turn into something you get tired of much more quickly because it's false. And I think that there are two sides to this. I think on the one hand, we should make gear that people like. On the other hand, I think we should make gear that people also can learn through and develop a deeper understanding of what they're into and ultimately the music and so on. So for me, I prefer music that has not necessarily been well recorded. I listen to a lot of 70s live recordings and to be honest, it's a very effective way of scaring people off if I'm that.
Probably.
But I think what really is telling about this is that if the system is really good, you can hear all the limitations of the recording.
Yeah,
but
also
you
the
can
purity.
Also hear what the musicians are doing and what's going on. So you can also hear all the good things. And I think this is really what we should strive for is systems that are transparent in a complete sense, meaning that you can actually, you as the listener can choose to what you want to listen to, not that the system is telling you, oh, you need to listen to this hi-hat because imagine this is really standing out because something is not right. But then the other side, I think, is also that we when we perfect this, and I know this also from some of my speakers, is that when you go as far as we can, you start to hear things from other things in the system that people maybe have not noticed before. And that means that we also experience some learning curve amongst our collaborators, sellers, resellers, and also the customers that don't blame the messenger. But I just feel that there is so much gear in the market that is in the business of compensating and making everything pleasant that I don't think it's correct for us to make something less correct than what we can do. And that is, we know this is not for the mass market, and that's fine. That's absolutely fine. But we rather want to be very, very good and understood for what we are good at. And then the right customers can choose us as kind of a very pure version of that direction. And then if they want something different, there will be so much other choices in the market. So it's also kind of I think it's an ideal, which some may say, why don't you just make it a little bit warmer and a little bit more laid back and blah, blah, blah. But then what's the difference between what we do and so much else? So I think it's obviously a matter of also where you want to go. So that's also why we have some ranges where we don't want to deliberately make something worse, but we always want to make the best possible out of the resources and the materials and so on that is available, so that you can.
But they all say that. They always want to build the best for the money, of course. So
of course, and we all think we do that in each our way. We just do it in different ways, and that gives different results. But I think from our perspective, the truth is that we may not necessarily want to sell our most expensive products to everybody because it's probably too extreme. And then maybe something in the middle or on the entry level might actually be what makes you happy as a listener long term, because they really sort all these serious problems in the same way. They are just not as revealing. And maybe at the end of the day, it's about that balance where I think you should never reveal the limitations of the source.
No.
So if you have let's say a good but not excellent source, don't put it up with the best and most revealing cables and speakers, because it might be impressive at first, but I think long term it's better to have a source that has the upper hand.
It's all about the balance. But
Exactly.
okay, because now we're talking about this is mostly your view and philosophy about creating cables and speakers. But
Yes.
I think it would be interesting for our viewers to know what the difference is between an analog interlink and a digital interlink. And let's just start out with coaxial, because that's the easiest cable to explain. So you have speaker cables, analog interlinks, balanced, single-ended, and of course also digital cables. How did you come to a product? I mean, what is your philosophy concerning digital interlinks?
Yeah, so I think digital interlinks is particularly interesting because the first thing we have to recognize is that even digital signals are analog.
Absolutely.
The cable is analog, the devices are analog, everything that actually transmits, modifies, stores, amplifies, whatever, is analog. So we are kind of in a weird situation when we deal with digital signals, because nobody has ever heard a perfect digital rendition, because no analog device or cable or anything can actually reproduce a square wave, which would be what a digital signal theoretically is built on. It's either
you can get close, but it's never perfect.
So I think the first thing to recognize is that digital might be in some ways considered perfect in a theoretical version of it, but in any practical implementation, it will never be. It's just not possible. Where an analog signal, in principle, would never have a square wave in it, because there's just nothing that occurs that way in nature. However, the square wave is a perfect stress test for like what is the transient response and so on for a system. So I think the square wave is an interesting problem, because in principle we cannot solve it, but then it's also a stress test that tells us about what is the dynamic behavior, especially also in the time domain, for any cable, whether that's analog or digital. So in our way of looking at it, in order to do analog cables as well as we wanted to, we kind of needed to make them so good that they might as well transmit digital signals.
But let's first explain what a square wave actually is, because a lot of people think it's just one signal that is with a very steep, we call it flank in Dutch. I don't know the English word for that, but it's like a square. Like a step. If you put it on a scope, you see like a square, a step. But what is it built of? Because there is no signal that is actually square.
Yeah, so it's sort of like the difference between math and physics. Where in math you can define something where it jumps instantaneously from like with where there's basically zero time interval between, let's say, an absolute zero and then a defined level. Let's call it 1. So in math, we can define something like that, but in reality, there will always be a transition time. There will be a transistor that needs to switch from one state to the other. There will be parasitic components of the circuit board of anything. That means that we cannot actually switch from one to the other without considering that there will be something going on in that transition where we actually see a continuous development of the signal from one state to the other. But that is different actually from the theoretical outset, which should have been from one to the other without a transition. Or a transition that is infinitely fast, meaning that there is no transition, it's just a jump from one state to the other instantaneously. So I think the square wave has to be understood as a step response in which you switch from one level to another without any time lag or anything. And any analog system, whether that's what happens inside a computer or a cable, will have parasitic components, meaning that there will be some time lag, and there will be some dynamics, which at first could be something that delays the rise time a bit. Second of all, you can have an energy storage, which is part of why that delay occurs, that then also can release some of that excess energy afterwards. So you can even have ringing. So when you see a step response, then just getting something that reacts quickly is just one part of the problem. The next part of the problem is then what happens? Just stop and go straight, which is what we want, or is an overshot and then an afterplay. And then again, when you drop it again, it's like, how is the tail and the drop? So one of the problems here is that you kind of have to, oftentimes you have to choose between the ability to react quickly on the one hand, and then on the other hand, the stability of the system. So imagine a jet fighter. NASA did some tests many years ago where they pointed the wings from backwards to forward to create the ultimate unstable aircraft, because that would mean that it without computers would just fall to the ground. However, it meant that it would be able to react so amazingly quickly to input responses, whereas a very stable aircraft like a
it takes time.
It's built to react slowly because that gives the stability. So we kind of have these sort of like different things where we want something that doesn't overshoot, ring, and is kind of uncontrollable. On the other hand, we also want something that reacts quickly. Combining these would be the perfect way to achieve this. It's just not that easy.
No. But how does a cable influence the signal? Because I noticed, for example, most measuring systems work with 50 ohms. If you use a 75 ohm coaxial interlink, you get artifacts because the impedance doesn't match. That's just one example of how a cable can influence a signal. But I think for a lot of people, this is like voodoo black box stuff, like a cable is a cable, but it actually isn't. And in a digital system, that can actually result in artifacts, in conversion errors and stuff like that. But how can you explain what happens there if there's an impedance mismatch or capacitance issues or anything like that?
Yeah, so there are different aspects to the problem. I think one is that we kind of need to understand that the parasitic characteristics of any cable, any component, be that we will have some self-inductance, we will have some capacitance, and there will be a DC resistance. Those will create some time domain coefficients, which basically determines the ultimate reaction time of the system. However, it also determines the energy storage and ringing, artifacts and so on. So that concerns you can say, any discrete point in a cable's ability to convert these things, also how it defines the characteristic impedance, which is sort of like something we can calculate out of this. But this is sort of like when the signal has to go through the cable, the capacitance would kind of make it seem like the resistance or the impedance is lower. However, it's a shunting ability that actually spills some of the energy into the storage, as opposed to the inductance, which would kind of elevate the impedance. But then it's kind of like then the energy kind of stays in the conductor, so to speak. So imagine that we have pipes, and those pipes are just never completely sealed. There will be some leakage. So if you have a high capacitance transmission line, there will be much more leakage. If you have a very low capacitance, then you kind of keep the energy inside. However, then you have the mass of all that fluid going through that then will react as well. So we have these different parameters that will kind of condition what happens dynamically. So that's one problem, which any change in state will be conditioned by. Then the other problem, and this is something I think when you're talking about impedance matching, is that any change in these parameters are not just a change that should be seen as, well, what is the total amount of capacitance, what is the total amount of resistance, and so on, but it should be understood that when we transmit signals, it's not one long row of electrons slowly walking through as a DC. Rather, it's a shock wave. So it behaves in some ways more like a light beam that is being kind of sent through, not as a matter of matter moving through like the electrons, but rather as a force of energy that then is a wavefront. And when that wavefront meets different conditions, it will change. And those changes will both affect what then continues onwards and the speed and all of that. However, changing that also means that typically you get a reflection backwards. So any change in this system, whether that's how you solder the conductor to the plug, or how the plug then kind of connects to the socket, and or if the cable somehow has been bent a bit, like any of those changes will have a potential to change the characteristic impedance, or in other words, the conditions through which the shock wave can then actually pass through the system. So
that's quite complicated if you think about it.
It's super complicated, and you kind of have to focus here, because at the end of the day, can we make this more smooth with less changes? Probably we're going to solve some problems that we would otherwise find very difficult to solve afterwards. That said, whether the cable is perfectly 50 ohms or 75 ohms, in my opinion, it is probably less important. The more important thing is that you don't have the changes throughout. And then, of course, the system in which it's like, if you have a receiver that is dimensioned for 75 ohms, that will have an influence on what then happens at that gate. But that's because of that design, not necessarily because digital signals naturally prefers one or the other. I think the changes throughout the system and this kind of characteristic changes, difference in characteristic impedance and so on, this is the fundamental problem that we, at least with digital signals, see even more so of, but it's not fundamentally different for analog signals, to be honest.
Yeah, I don't know about the characteristic impedance. I mean, I measured a lot of digital cables on my systems, and you actually see if there's a mismatch that the jitter goes up. I think that is audible. Some people say you can't hear 2 or 3 picoseconds of extra jitter. I disagree. I think we're very, very sensitive to.
Well, I agree with that.
To jitter.
I would argue that once we define something at jitter, it's already too late.
So absolutely.
So the jitter usually is defined as you have sort of like a change in the information.
Yeah.
However, I think that what also goes on is that even if that information is accepted by the digital system, it can still be time modulated. So that even without having detectable jitter in the sense that we technically define it, we have manipulations that are still affecting, and this is why we have an endless battle to fight in the digital domain. Like how do we care for switches and streamers and all of that way before we even have a signal to feed the DAC chip. And then we end up realizing that, well, the DAC chip is maybe the least important insofar that it's kind of okay. But we figure out that the whole range of things going on before then are just of immense importance.
Yeah, it's just a side story. Martijn and I were testing Volumio, no, not Volumio, Orevana software. And we installed it on 3 different computers. A Raspberry Pi, an Intel NUC, and another mini computer. So the software is the same, the computers are different, and you can hear a huge difference between those three computers. Now, how do you explain that? And it wasn't small differences. It was very obvious in terms of timing, smoothness, detailing, layering. I was like, okay, I'm a computer guy. I know how they work. And I was like, how is this actually possible? Because if you record the outcoming digital stream, they're exactly the same.
Yeah. And then yet they're not.
Yet they're not. That's why I thought you are absolutely right about trusting your ears, because I could do a blind test and just point which computer is playing. It's that obvious.
Yeah. And I think this is actually really like hitting it on the head, like that we know that if we kind of look at the information in the formal way that we have learned to do, so it's amount of, we have ones and zeros, and then when we do the checksum and all of that, it's all good. But then you have to be quite thick-headed to not acknowledge that it just doesn't sound the same, and the differences are in any aspect. It can be the timing, the energy, the balance of the entire system sounds different. Like it's like as if there is no limit to the perceivable differences, even though the amount of information is the same. If we don't think about the time domain.
I think it's right in there, along with, because every computer has a different noise output. For example, I mean, if you just look at the data, like you said, it's exactly the same. And it's the same with every digital cable as well. And that's why this is an interesting topic. But there's much more going on. If I would look at the noise patterns that leak through the USB port or through the Ethernet port, they're all different.
Yeah.
So how does a system handle that? How does it influence other clocks in other gear in your system? How does it influence the preamp or the power amp or any other cable that's laying next to it? It might be small, but we're both hi-fi nerds anyway, so we play with very transparent systems that actually reveal that kind of stuff. And I think a lot of people don't look at all the side stuff that's going on in a system, like electrical noise, magnetic fields. I don't know. I can think of a lot of stuff that we don't look at.
And to be honest, one of the problems is that it becomes a bit endless once we start to look at it. So we kind of need to be aware of the big problems and then focus on those first, because then otherwise we just lose our minds, to be honest. I remember way back when we started to get all these modern electrical light bulbs that are not working by just heating an element, but rather working through a much more, I would say, ingenious way that saves a lot of energy. However, the noise spectrum of those were then also incredible. So I remember that I had a big problem for some time, because introducing those light bulbs in our apartment, I just couldn't get the sound of the system to be anywhere near what I could live with. At first I kind of had to go back to old and find sort of like stock of old light bulbs just to kind of cure it a bit. And then I guess that the light bulbs have become a bit better, so the noise spectrum it's not affecting as much, or maybe we just learn to live with it or something, because at the end of the day there are just factors that are way beyond what we hi-fi people live with. But to get back to your question, I think it's really spot on that we have so many aspects in so many things, both in the system and around the system, that affects what's going on. So if you imagine that we talk about the time domain, and in a digital signal, the time domain that is really critical could be seen as, when is the receiver detecting the switch from one state to another? When we have a square wave, it might look very simple. Then obviously that's when it switched from one to the other, but it has to, at some point, say, now the switching is happening and has been done.
Yes.
And that's not necessarily as simple.
No.
If you then have noise that is basically also infused to this system, you can kind of see that the square wave is not just a square wave. Now you have all sorts of analog and switching noise kind of going in, modifying this. So when that switching is going on, could actually be tilted one or the other way due to this noise infusion. So there you have a very direct causality between having a very complex signal going in, of which some of it is the digital information, and then you have to have a receiver that somehow can detect what is the information switching point, as opposed to whatever that signal is doing at that point in time, which is just really difficult to control. So I think that's one aspect. The other thing is that in digital, we need chips, we need processes to actually convert, let's say, something which is stored as a file into a bit stream of some sort, and we need to do that, and there will be error correction, there will be all sorts of things. So when we take a laptop, it has enormous computing power, but the problem is that it's really difficult to control the prioritization of how that audio bit stream is being taken care of, because in most cases people would care more about other systems than the audio stream, which is very secondarily. So I remember back in the day when USB converters became a thing, and I bought my first one and I put it into my laptop, and it was like, oh my God, this is crap.
Yeah, I know. The first ones were bad.
But at the end of the day, I found out that the DAC itself was not so bad. The problem was that I needed to do a lot of work on the laptop to get that as a streaming, like the kind of the computing platform to behave in a way that gave an acceptable output. So that was about the streaming software. That was about how to optimize
buffering,
the computer
all that kind of stuff.
So I really know from back then that how much all these seemingly small things can matter. And put on top of that the noise problem, which is that any component will have a noise spectrum, and that will also be part of the whole thing. So yes, digital is very interesting because it's one and zeros, and then it's one and zeros that have to be very accurately processed in the time domain, which I would say we have to just acknowledge is impossible to get 100%.
What is the biggest influence in a digital cable? Is it capacitance? Is it inductance? Is it the connector? Is it how did you design your cable? What did you keep in mind when when you were working on it?
The really interesting things is that during the early development, I found out that the same cable design and construction had similar sonic attributes, almost no matter how you used it. And this was kind of like, well, the impedances are different and the information is different, and like this makes very little sense until you realize that it's because these combinations of parameters and other things, also the mechanical domain and so on, all of that will kind of modify whatever's going through, whether that's AC from the wall or whether that's a digital signal or analog signal. And our ears are just apparently so incredibly sensitive to these time domain changes that we can pick it up almost no matter what that cable is used for, insofar that it's coupled into the system and somehow in some critical way either processes information or power or something like that. So I would say that the difference between optimizing for the analog and for the digital was more consequence of being more attentive to certain parameters, so that we can kind of get that coherent smoothness, so to speak, of the transmission line even more perfected for the digital. But the fundamental parameters, we already kind of knew what we were looking for, because at the end of the day, they had a very similar effect I would just say maybe just more sensitive in the digital, because the signal is more sensitive to timing distortion, because you have a fast switching square wave signal, which then is an ultimate stress test. So basically, it I would say everything is important. My hunch is that the low capacitance is of very high significance, because the capacitive part will always define the ultimate bandwidth.
That's what I was pointing at. Exactly, the capacitance is important in this case.
Yeah, and the signal transmission speed as well is also helped vastly by having low capacitance. So I think that whatever we do, low capacitance is always what we go for.
So for our viewers, we had a slight disruption in internet. It was on our side, I think, because it was like, and it was gone, which proves that digital isn't bulletproof at all. But we were discussing the influence of capacitance in a digital cable, and we both agree that high capacitance in any cable is a bad idea. Because it influences timing and influences speed, which we already measured in our big comparison test, that the higher the capacitance, the higher the propagation variance. That was very easy to link, because all cables with high capacitance had high transmission variables in the cable. So that
it makes sense.
It makes perfect sense.
Imagine you are a shockwave of energy wanting to kind of pass through a cable. Then high capacitance would be the equal of that. You have to charge a whole row of batteries all along the conductor in order to be able to pass the voltage signal on to the next. So the less you have to do that, the faster you can charge it, and the less strain you're also putting on the transmitter, and the faster you're getting that voltage signal in a less modified manner to the recipient. And for digital, as we talked about, it should be square waves, but then because of, for instance, capacitance, you have this, that you have to charge the sort of like the cable before you can even pass through the signal. That means that you're kind of moving away from the perfect square wave, and then you're rounding the corners and delaying, and also potentially causing overshooting.
True. I actually showed that. No, I didn't show it. I could see it in the measurements, that the square wave becomes much more round as soon as you have a high capacitance cable. But do you use a coaxial layout for your digital cables or not?
We don't reveal the exact topology, but actually we don't use a conventional coaxial. And one of the problems, and this also comes to the question of screening, is that in a coaxial cable, you have certain virtues that are really good. For instance, that you can say that the ground screen that is also the signal return is obviously going to insulate the actual signal transmitting conductor very well. However, the problem is that that you then also have currents that can actually move about in that screen that you have very little control over. So the whole time domain question then becomes something where you can design something, but then what really happens under dynamic conditions will be something quite different and significantly more complex, which almost always is a very bad thing when it comes to audio. So for us, it's a little bit like designing a circuit. In a circuit board, there is a habit of just having a huge ground plane, because that should lower capacitance and it should also minimize the inductance and so on. The problem is just that you really need to steer the exact kind of signal path through which the current is moving backwards, because when you transmit a signal, you kind of need to take care of both the signal out and the return, because they condition each other. And if you can't control one, you basically cannot control the other. So what we do is that we control both the signal the signal transmission line and the return through the same geometry, because you kind of need to do that. Otherwise, you're actually not in control of the signal transmission.
Mm-hmm. I'm very curious about the topology now, and how you screened it, because we discussed screening a cable in another interview, because that's a whole topic in itself, whether or not to actually screen a cable. Just like loudspeaker cables, it has perks, but it also has downsides. But I think for now, the digital cable discussion is quite obvious. It's digital, but it isn't, and there are a lot of challenges, to overcome. I completely agree on the capacitance story. Lower capacitance is just better in almost all cases, I think. I think for the next topic, it would be interesting to look at power cables, because that's a very, very interesting discussion on all hi-fi forums, I think. Some say current is current and energy is energy, but I don't agree in this case. But it's very hard to prove. But thank you for now. And let's discuss power cables the next time.